come back to this second half of today's lecture. As I said that now we will discuss some topological properties of the Zariski topology. So, let me just recall or mention that what was our situation. Our situation was L over K field extension and then we have defined these maps VL. These maps are defined from R root ideals or radical ideals of A. I do not want to call it A, we have not called it A earlier. So, and R is the ring which is a polynomial ring in n variables over the field K. Then we have this map from the root ideals of R, radical ideals of R to K algebraic sets, K algebraic subsets in L power n, and also we have defined the map in other direction. This map is denoted by IK, and this we have defined it for arbitrary set. So, anyway, our results are better in the sense that this gives a topology on L power n. So, we consider L power n, Zariski topology on L power n. The Zariski topology is defined by saying that closed sets, closed subsets in L power n are precisely K algebraic sets, K algebraic subsets in L power n. So, that is how we have defined closed sets, and we have checked that they satisfy the required properties of the closed sets in a topological space. That means empty set is a closed set, whole space is a closed set, arbitrary intersection of closed is closed, and finite union of closed is closed. So, these properties are satisfied by these algebraic subsets, and therefore, they form a closed sets in a topology on L power n, and that topology we are calling it Zariski topology. These were defined by Zariski. Alright, so we have, so really one should think that you have defined a map from VL from the radical ideals of the polynomial ring to the closed sets in closed subsets in L power n, and the map, the converse map IK, converse means the inverse, we have given the other way map, and these two maps are inverses of each other only when K is algebraically closed. So, K algebraically closed then VL and IK are inclusion reversing bijections. In fact, inverses of each other. This is very important. This was precisely HNS 2. HNS 2. This follows from HNS 2. So, this allows us to study topology on the Zariski topology on L power n in terms of the radical ideals in the ring, polynomial ring, and therefore, it gives a interplay between the ideals on one side and on the other side these K algebraic sets or closed subsets in the Zariski topology on L power n. Also, in particular, when L equal to K equal to L algebraically closed, this is a special situation. In that case, we are even better, then the points in this L point, the points in L power n, they corresponds to the maximal ideals. In the polynomial ring. L is k equal to L, so I should be strictly writing this k power n. This is k power n. So points give the maximal ideals. So this is precisely what classically maybe more than 200 years or 100 years back the algebraic geometry was studied in this way, but this language did not exist in a precise way those days. Therefore, there were lot of confusions. I will tell you one of the confusion when I have enough vocabulary with me. Anyway, so the point to note is that when L is algebraically closed, then there is a nice correspondence from geometry to algebra and algebra to geometry. And this correspondence we are going to study more and more, and this study precisely is algebraic geometry, because lot of geometric problems you are going to prove by using algebra and some algebraic problems you are going to prove by using geometry. And this is precisely this study is precisely algebraic geometry. But obviously there are some difficulties in this. I will note down the difficulties after I finish. So now you might ask, in this situation, for example, what will, and also actually we have also analyzed points in Ln, what happens to them, what do they correspond to, and we know they correspond to some ideals, and then in the last lecture we have given some corollaries which describe them, when are they maximal ideals and so on, and the closure and so on. So I am going to do that more now. I will not assume k equal to L, but I will certainly assume L is algebraically closed. That is because I want to use these null standards. Without null standards we cannot go and come back. Alright. So, so I want to describe now what happens to the prime ideal, what do they correspond here to, what subset do they correspond to. So alright, if I take a prime ideal P here, suppose I take P, a prime ideal in the ring, polynomial ring R, then what do they correspond to? Obviously this map is VL of P. So what kind of this is, of course this is a closed set, this is a closed subset in L power n, that is by definition. But what kind of a closed set it is, and can you recover? Of course you can recover back this because of the null standards. If you assume your L is algebraically closed, then you can recover back this, because we know we have proved in HNS2 that Ik of VLP, this is the radical ideal of P, but that is P because P is a prime ideal. So you can recover back. But I want to explain more what kind of a subset is this. It's a closed subset is fine, but does it have some more properties, because this P is a prime ideal. For example, if I take arbitrary ideal, what is the difference between this closed set and if you take the arbitrary ideal and take VL of that, this is also closed set. So what is the difference? That is what I am going to explain in the next. Okay. Also one more thing to note that I will write on the next page. One more thing to observe, that if I take ideals of the ring R, that with inclusion, this is a lattice, that means it is an ordered set, and any two elements have the supremum and any two elements have the infimum. Such a ordered set is called a lattice, that we have seen earlier. And also if you take the closed sets, closed subsets in L power n with the natural inclusion, that is also lattice. So that is, it is ordered set. Ordered set is clear because ordered set is with the natural inclusion. And what is the supremum and what is the infimum of two of them? In fact, the supremum should be the union and infimum should be the intersection. And this makes sense in a any topological space. If I take the closed subsets that form a lattice, and the map we have given, this map. So VL, so even the radicals, that is also a lattice, because you can take, you can appropriately define supremum and infimum there, and this map VL and IK, these maps are actually lattice. It doesn't keep the same order, but it is anti-isomorphism of lattices. So this VL and IK, they are anti-isomorphisms of these two lattices. Anti means they change the order. Alright, so we are studying this now. You have noted in Hilbert basis theorem that the polynomial ring R is a Noetherian ring. That means equivalently the set of ideals satisfy ascending chain conditions on the ideal. So what will happen here, that if I take the corresponding images, that will satisfy the descending chain condition. So maxima will become minimal and so on. I will make these more precise in the statements now. So that is what we are heading to. So we are studying now Zariski topology on L power n, and I will assume L is algebraically closed and L over K field extension. Actually, not all the statements down L algebraically closed is needed. It is needed only when I use Hilbert-Null standards. Then only it is needed. If there is no use of Hilbert-Null standards, if it only uses these maps and their properties that it is inclusion reversing and so on, then algebraically closed is also not really necessary. So first is a definition. This definition is standard in a topological space. So a closed set, closed subset V in L power n. Of course, when I now say close, open, etc., that will be in the Zariski topology. So a closed subset V in L power n means this V is a K algebraic set. That means what? That means this V is of the form V of VL of some ideal. So that is what it is. So when I want to stress more on the topology, I don't write this K algebraic set. When I want to stress more on algebra, I will write this, because then it will involve an ideal. So this is a closed set in V in L power n is called irreducible. If first of all it cannot be empty set and it cannot be broken into union of two closed sets, and if V equal to V1 union V2, where V1 V2 are closed in L power n, then either V1 should be equal to V should be equal to V1, or V should be equal to V2. So therefore it is called irreducible. So now the next proposition will describe how do you test some subset in Ln is some closed subset is irreducible or not. So I will write, so proof proposition okay, let V be a closed subset in L power n, then V is irreducible if and only if the ik of V is a prime ideal in R, and R we have always denoted by the polynomial ring over the base field K. So this is very nice. So irreducible closed subsets correspond to the prime ideals. So we are improving the dictionary which is given to us by these VL and IK maps. Alright, so proof is very simple. Proof. So let me put, let A is IK of V. This is an ideal in, this is a root ideal in R, radical ideal in R. We have noted that earlier. In fact, this is precisely what? This is intersection of all IA where, so we do not need that. So why unnecessary break our head? So we do not need that right now. So it is a radical ideal by definition, because this is precisely all those polynomials, whatever the definition, all those polynomials capital F in R such that F should be 0 on every point of V. So this, if some polynomial vanish at every point of V, then the power also, if power vanishes on every point of V, then that polynomial also vanishes, because we are in a field, L is a field, and therefore it's a radical ideal. All right. So now what do we know? So we know that if I take VL of IKV, I say this is nothing but V, because see this is very easy to check. In fact, this was one of the property I stated, that was I think property number 6 or some property. This V compose I, VL compose IK, this is identity on closed sets. So anyway, so I would simply here a note here, this is one of the property and which did not need L algebraically closed. So this is very easy to prove. So what do you have to prove? Any element here is here, and what is the definition of here? That means that element, all these polynomials should vanish there, but that is precisely a definition. So this is clear. So because V is non-empty, since V is non-empty, so that means what? So that means 1 cannot belong to this ideal A. 1 cannot belong to this. If 1 belongs here, see this is VL of A, this is equal to VL of A. So if 1 belongs here, then that means this will be empty set, but this is not empty set given. So it is a proper ideal. So that is A is a proper ideal in R, and I want to prove that this A is actually a prime ideal. So, to prove that A is a prime ideal. In R. Remember, we are proving which implication? We are proving this implication. This implication we are proving. That means we are assuming V is irreducible and we want to prove A is a prime ideal. So, our assumption is V is irreducible. Suppose that V is irreducible and I want to prove it is a prime ideal, the ideal of V, this is a prime ideal I want to prove. So, that means what? If a product belongs to A, then one of them should belong to A, and A should be a proper ideal, which already we have noted A is a proper ideal. And now suppose the product F times G belongs to A, where F is in R and G is also in R. So, I now denote the elements in the ideal by these letters F and G because they are polynomials. Alright, and consider, and we want to prove that. So, what we want to prove? That either F belongs to A or G belongs to A. This is what we want to prove. This is what our goal is. Alright. Okay, now and consider now hypersurfaces H equal to VL of F and H prime equal to VL of G. These are two hypersurfaces, these are closed sets by definition, because this is algebraic set, K algebraic set defined by the polynomial F, this is algebraic set defined by the polynomial G. And then what happens? Then we are considering, look at V, given V, that is same as H intersection V union H prime intersection V. Let us check this. How do we check this? So, look at, start with this union. So, I am proving this. So, this one is what? Let us write down. So, this is V of A, VL of A, this is VL of A, and this is VL of F. So, this is VL F intersection VL A, and then union VL G intersection VL A. But what were the properties of these closed sets? This is again equal to VL of somebody, and that is VL of whom? This is VL of ideal generated by A and F, and this is union, this is ideal VL of ideal generated by A and G. This was the property we have noted. This is very easy to check. And what is the union then? For union you have to take the either intersection or the product, it is same. So, this is VL of AF ideal generated by AF multiplied by ideal generated by A and G, that is union corresponds to the product or intersection, but intersection and the product also will give you the same VL. Alright, but what is this ideal? When I take the this is generated by, of course, A square and then A times F and A times G. So, anyway it is contained in A and this is Fg, but so this is equal to VL of A. That is because this equality, because F times G, this belongs to A. And here we have used the fact that whether I take VL of A square, that is same thing as VL of A, or VL of A cube also. So it does not depend on the ideal, but it depends only on the radical. So therefore these are equal, but this is same as this. So you see here we wanted to prove this, we started with this and came back and proved this. So we have proved, therefore this is proved, this is proved, and this is okay. So this is proved. Now but we are looking for this, but now see this VL, we have proved this equality, and this is a closed set, this is also closed set, and V is the union of the two closed sets, but V is given to be irreducible. That means V cannot be, so therefore V has to be one of them. So that implies either V equal to H intersection V or V equal to H prime intersection V, one of them. So if it is equal to this, then so if it is equal to this, then this means V is contained in H, and then if V is contained in H, then you look at the ideals. So this will imply you take the ideals on both sides, that will reverse the inclusion. So Ik of V will contain Ik of H. Ik of V is the ideal A, we have called it, and F belongs to the ideal of H, because H was defined by F. So F vanishes on H, therefore F, polynomial F will belong to this. So this equality means A belongs to F. Similarly this equality will mean G belong to Ik V, which is A. So we have proved, assuming irreducibility, we have proved that the ideal is prime. So that is, this Ik V is also called the ideal of V. Alright, so now conversely, suppose that A, which is Ik V, is a prime ideal. Then I want to prove V is irreducible. So first of all, we are assuming V is non-empty, right? So that is we have to show V is irreducible. First, this is a prime ideal, therefore A cannot be the whole ring. Therefore V is non-empty, because V is precisely VL of A. So it is non-empty because A is non-empty. This was if it was empty, then the ideal will be the whole ring. Alright. So here also we have not used null standards, remember that. Now suppose V is the union of two V1 union V2, and V1 union V2 are closed subsets in L power n. Then I want to prove V is either. So to prove V equal to V1 or V equal to V2, this is what we want to prove. This is the global. Alright. So we suppose we are assuming this. So let us take ideals on both sides. So A equal to IKV, which is, and Ik of the union, Ik V1 union V2 is precisely Ik V1 intersection Ik V2. This is the property of Ik. This is very easy to check again, just check an element here and take it is here. So, and this intersection will contain the product IKV times IKV1 times IKV2. This is also easy, product is contained in each one of them, therefore, it is contained in the intersection. But now A is a prime ideal, A is given to be prime ideal, and these contain the product of the ideals. Then I say A has to contain one of them. So, that implies A contains IK V1 or A contains IK V2. This is because A is a prime ideal. This implication. That is very clear, because if it does not contain both of them, then you take an element here which is not here and take an element which is not here and consider their product. Product is here which is in A, but product is not in. Alright. So, that shows this, but what does this implication mean? So, now I apply V again. If I apply V, VL of A which is V, and which is now this will get reversed. So, this will be contained in VL of IKA IK not IK, IK V1 but what is this? This is V1 I say. I have used that earlier in the earlier proof also. V compose IK is good, V compose IK is easier to do it, but IK compose V is not easier. So, this is easy. This is also you can see V1 is obviously contained here, and these points of V1 vanishes here and so on. So, this is again and again we will use this. This does not use Hilbert-Null standards. I want to stress on that. So, this implication will give this, and the other implication. So, or V is contained in V2, that is what we wanted to prove. So, therefore, we finish the proof of this. Now, the next one is, I will note it. So, under that prime ideals will correspond to the irreducible closed subsets. So, the next proposition, closed subsets in L power n satisfies DCC. So, what does that mean? That means in our earlier language, if I take the closed subsets, so that closed subsets. So, let me introduce a notation for that, because we are going to use again and again. So, the closed subsets I want to denote by F and Z for the Zariski topology and L power n. This is the set of all closed subsets. Subsets in L power n, which is also same as K algebraic sets. Alright, that satisfy DCC means what? That means, so this means Fz L power n with respect to this is an Artinian ordered set, which is equivalent to saying it has a minimal property. That means every subset, non-empty subset of Fz L power n has a minimal element. So, that means what? That means when you translate into the closed set language, that means every subset of closed subsets has a minimal element. All right. So, proof. So, consider a descending chain. So, that is V1 contained in V2 contained in V3 and so on, and I apply Ik to this chain. So, that implies Ik V1 contained in Ik V2. So, we get an ascending chain of ideals in the ring R, which is a polynomial ring, and we have proved it is Noetherian by Hilbert basis theorem. So, therefore, the chain should be stationary. So, there exists, so that implies there exists N naught such that Ik Vn equal to Ik Vn plus 1 and so on, all the way they are equal. So, it became stationary, but then apply V to this. So, applying VL, we get VL of Ik Vn equal to VL of Ik Vn plus 1 and so on. But then this is Vn, this is Vn plus 1, therefore, these are equal, and so therefore, the chain is stationary. That means it satisfies DCC, and equivalent that it is minimal, that always that we have proved for arbitrary Artinian ordered set. DCC is equivalent to the minimal property. All right, with this I will stop today's lecture, and I will continue studying the topological properties of the Zariski topology on L power n, and eventually I will point out the difficulty in carrying it on further. So, that will allow us to think a better option than the this K spectrum and so on. So, we will generalize this, and in the generalization things will become easier, but on one hand, but the definitions are more abstract. So, this will lead to abstract algebraic geometry. All right. So, with this I will stop, and we will continue in the next lecture. Thank you.